Every device you own is running on technology invented before the internet existed. Lithium-ion batteries powered the modern world for 30 years, but they were always a compromise. They catch fire, they degrade, and they top out far below the energy density we need. But right now, in labs and in the first commercial vehicles on the road, something has fundamentally changed. Solid-state batteries don't improve on lithium-ion, they make it obsolete. This is the energy revolution that changes electric vehicles, the power grid, and civilization itself. Hit subscribe because the energy revolution doesn't stop here. To understand why solid-state batteries matter, you have to understand what we've been living with. The lithium-ion battery was commercialized by Sony in 1991. It was a breakthrough. Compact, rechargeable, and energy-dense enough to untether us from the wall. It powered the first laptops, then mobile phones, then electric vehicles. The entire portable technology revolution runs on the same basic chemistry. But lithium-ion was never perfect. It was just the best option we had. The core problem is the electrolyte, the material inside the battery that moves charge between the two electrodes. In a lithium-ion battery, that electrolyte is liquid, and liquid electrolytes are flammable. That's why phones catch fire. That's why electric vehicles have gone up in flames on highways. It's not a manufacturing defect, it's a chemistry problem. Liquid electrolytes also degrade over time. Every charge cycle breaks them down slightly. After a few hundred cycles, you start losing capacity. This is why your 2-year-old phone holds less charge than it did on day 1. This is why EV battery packs are rated for a limited number of cycles before degradation becomes a real cost. And then there's the energy density ceiling. Liquid electrolytes physically limit how tightly you can pack energy into a given space. For EVs, that ceiling is the difference between a 300-mile range and a 600-mile range. For grid storage, it's the difference between powering a neighborhood and powering a city. These aren't minor inconveniences, they are fundamental limits baked into the chemistry of every lithium-ion cell ever made. Scientists and engineers have known this for decades. The question was never whether we needed something better. The question was whether we could actually build it. The answer, it turns out, was always in the electrolyte. Replace the liquid with a solid, and the entire equation changes. A solid electrolyte doesn't burn, it doesn't degrade the same way, and it unlocks energy densities that liquid chemistry simply cannot reach. The principle has been understood since the 1970s, but building a solid electrolyte that actually works at scale, that took another 50 years. So what exactly is a solid-state battery, and what makes it so different from everything that came before? At its core, the architecture is similar. You have 2 electrodes, an anode and a cathode, with a material between them that conducts ions. In a solid-state battery, that middle layer is a ceramic, glass, or polymer solid, not a liquid. That single change rewrites the rules. First, no flammable liquid means no thermal runaway. The leading cause of battery fires is eliminated at the chemistry level. Second, solid electrolytes are stable at higher voltages. That means you can use more energy-dense electrode materials that liquid electrolytes simply can't tolerate. The result is an energy density that can reach 2 to 4 times what lithium-ion achieves today. Third, without liquid degradation, solid-state batteries can endure far more charge cycles. We're talking thousands of cycles versus hundreds. And they charge faster. A solid electrolyte can handle higher current without the side reactions that damage liquid-based cells during rapid charging. Toyota has demonstrated a solid-state EV battery that charges from 10 to 80% in under 10 minutes. That's faster than filling a tank of gas. The solid electrolyte also operates across a much wider temperature range, meaning these batteries perform in extreme cold and heat where lithium-ion degrades rapidly. Taken together, safer, denser, longer-lasting, faster charging, and more resilient, solid-state isn't an upgrade, it's a category change. But knowing the theory and manufacturing it at industrial scale are two entirely different problems, and for 50 years, the scale problem nearly killed the technology before it started. To understand what solid-state batteries mean in the real world, forget the lab for a moment. Think about a truck driver in Montana in January. His electric rig loses 40% of its range the moment temperatures drop below freezing. A 300-mile truck becomes a 180-mile truck overnight. That's not a software problem. That's lithium-ion chemistry failing in the cold. The same reason your phone dies faster in winter. The liquid electrolyte inside the battery slows down. Ion movement becomes sluggish, the voltage drops, and the truck stops long before it should. Now put a solid-state battery in that same truck, same temperatures, same highway. The performance curve barely moves because there's no liquid to slow down. The solid electrolyte conducts ions efficiently across a temperature range that would cripple a lithium-ion pack. That truck gets its 300 miles back in January in Montana. Or think about a family in Phoenix. Their EV sits in a parking lot at 110 degrees Fahrenheit all summer, day after day. Every cycle of heat accelerates the chemical breakdown happening inside their lithium-ion pack. The battery that gave them 250 miles in year 1 gives them 190 miles in year 3. By year 5, they're looking at a battery replacement that costs thousands of dollars. With solid-state, that degradation curve flattens dramatically. The battery serving them in year 1 is nearly the same battery serving them in year 10. That's not a small improvement in ownership economics, that's a fundamental shift. These aren't hypothetical scenarios. They are the exact pain points driving billions of dollars into solid-state research right now. Toyota has committed over $13 billion to solid-state battery development. They are targeting commercial solid-state vehicles by 2027. QuantumScape, backed by Volkswagen, has been quietly solving the manufacturing problem for over a decade and is now producing cells at pilot scale. Samsung, Panasonic, and CATL, the company that currently supplies batteries to Tesla, are all racing toward the same finish line. This isn't a startup moonshot. This is the entire global battery industry placing the same bet at the same time. Every major automaker, every major electronics supplier, every national energy program with a grid storage problem, they are all pointing in the same direction. And the reason is simple. Whoever cracks solid-state manufacturing at scale doesn't just win the EV market, they control the energy future. The promises of solid-state batteries have been around for decades, but promises don't power cities. Data does. So let's look at what's actually been demonstrated. Toyota's latest solid-state prototype achieved an energy density of 1,200 watt-hours per liter. Current lithium-ion tops out at around 700. That's a 70% improvement in how much energy fits in a given space. QuantumScape published cycle life data showing their cells retaining over 80% capacity after 1,000 fast charge cycles. Most lithium-ion cells hit that degradation threshold in under 500. On charging speed, Samsung's solid-state research division demonstrated a full charge in just 9 minutes under lab conditions. 9 minutes for a full battery. Temperature resilience testing shows solid-state cells operating at full rated capacity down to -30 degrees Celsius, conditions that reduce lithium-ion output by up to 50%. Safety testing results are equally stark. Solid-state cells subjected to nail penetration tests, the standard method for triggering thermal runaway, showed no fire, no explosion, no rupture. That single result matters more than almost any other metric, because thermal runaway isn't just a consumer inconvenience, it's the reason entire EV model lines have been recalled. The product trajectory is moving in the right direction too. Solid-state cells currently cost significantly more than lithium-ion to produce, but every major manufacturer is reporting cost curves that look identical to early lithium-ion in the 2000s. When lithium-ion was first commercialized in 1991, a single kilowatt-hour of storage cost over $3,000. Today, it costs under $100. Solid-state is following the same curve, just 30 years later. The data isn't speculative anymore. It's peer-reviewed, investor-validated, and showing up in production timelines. Solid-state has crossed the line from research project to industrial reality. The question is no longer if solid-state batteries will replace lithium-ion. The question is how fast and who gets there first. Solid-state batteries aren't just a better product, they are infrastructure. And infrastructure changes civilizations. The internal combustion engine didn't just replace horses, it created suburbs, highways, global supply chains, and the modern economy. The battery is doing the same thing, just faster. Start with transportation. A solid-state battery with 600-mile range and 10-minute charging doesn't improve the EV, it kills every argument against it. Range anxiety disappears, charging infrastructure pressure drops, the last psychological barrier between consumers and electric vehicles collapses. Then there's the grid. The single biggest obstacle to renewable energy has never been generation, it's storage. Solar panels produce power at noon, people need it at 7 in the evening. Solid-state batteries at grid scale solve that mismatch. You store the noon surplus, you release it at peak demand. Renewable energy stops being intermittent and starts being reliable. That single capability, reliable grid-scale storage, is worth trillions of dollars and decades of geopolitical leverage to whoever controls it first. Which brings us to the geopolitics. China currently dominates lithium-ion battery manufacturing, controlling over 75% of global cell production capacity. Solid-state reshuffles that deck. The materials, the manufacturing techniques, and the intellectual property are still being written. The US, Japan, South Korea, and Europe are all investing heavily to ensure they aren't locked out this time. But with any transformational technology comes disruption, and disruption has losers. Oil-dependent economies face a slow-motion crisis as electrification accelerates. Nations built on petroleum exports are already modeling what happens when EV adoption crosses 50% globally. Lithium-ion supply chain workers, mining operations, and manufacturing facilities face a hard transition. New technology doesn't wait for the workforce to catch up, and there are legitimate questions about the raw materials for solid-state. Sulfide and oxide electrolytes require elements that have their own supply chain vulnerabilities. We are not trading one perfect system for another. We are trading a flawed system for a better one, and the transition will be messy, political, and expensive. But the direction is irreversible. The physics are too good, the economics are converging, and the geopolitical pressure is enormous. Solid-state batteries will define the next 50 years of human energy the same way oil defined the last 100. The only question left is whether the world builds this transition wisely or repeats the same mistakes it made with every energy revolution before it. That answer won't come from a lab, it will come from policy, investment, and the choices billions of people make about how they power their lives. Lithium-ion was never the destination, it was the bridge. And now the bridge is ending. Solid-state batteries are not a future technology anymore. They are a present one, moving from labs to production lines to the vehicles and grids that will power the next century. The energy revolution isn't coming, it's already here, and it's moving faster than most people realize. Every Thursday, we cover the science that is reshaping our world. This is SynthCosmos. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it, every single week. We'll see you in the next one.